So as we begin our discussion with complex roots and solving, there's kind of two levels of it. There is the mechanical computational aspect, which if you understood real distinct roots, it's going to be the same thing, just a different formula. Then there's the understanding why the formula is the way that it is. And for most students, that jump is very difficult because you kind of have to understand and feel comfortable with complex numbers and some very interesting formulas, namely Euler's formula, and how it's used to derive the um, aspect of the formula where there is no imaginary part. So there is going to be a jump in the formula where the imaginary I value disappears. And if you truly want to understand why that is the case, it's kind of a deeper dive into Euler's formula, how complex numbers work with sine and cosine. And it's just something that can't be covered in this lecture because it just requires so much extra information and derivations and understanding that it's a little too difficult. So I'm going to make a couple of things that kind of point you in that direction. But at the end of the day, if you truly want to know what happens to the imaginary number and how it becomes just sine, that is something that I ask you to investigate within the textbook and online videos and stuff like that, because I'm very sure that there's people who've made nice videos with visualizations of what's going on. It's just one of those things where, for the sake of this class, it's just too difficult to go over. So in the complex root case, what we're analyzing is we are looking at the case where b squared minus 4ac is less than 0, right? So if that is the case, you have a complex number. So this means R is complex and will have the form R equals, so we use alpha. You can use A, doesn't matter. So alpha plus beta I. Okay, so that's a complex number. Some people use the letter Z for complex. So this is our traditional complex number. Um, Now, what's interesting about complex numbers, or specifically complex roots, um, all complex roots come in conjugate pairs. That is, they always come with two, and they have a special property, and that is if you multiply them together, so alpha plus bi times alpha minus bi, they will always cancel out the imaginary component like that. So, if you've ever heard this, there is a difference rule for factoring with quadratics, but there's no sum rule for squares. No, difference of squares is true, sum of squares is not true. Sum of squares only works for imaginaries, so it doesn't work for reals, right? So, this is just conjugate pairs, complex conjugate pairs, right? So, if you use our structure, right? So, we know the solution to any homogeneous second order differential equation is y equal to c1 e to the r1t plus c2 e to the r2t, then y would just be equal to c1e to the alpha plus beta I times t plus c2e alpha minus beta I times t. Like, that's the solution. And if you wrote that down, you are not wrong at all. That's actually correct. However, there is a fundamental problem. This solution isn't very graphable because it has imaginary complex numbers. Complex number doesn't graph well in the real plane. There is a complex plane to graph numbers, but it doesn't. That's kind of a whole different aspect of how we analyze and we actually use vectors. So there's a kind of a fundamental problem here with this solution. It just doesn't work well for what we want to do, right? If you're just dealing with abstract stuff, um, then it's not really going to be useful, right? But is there a way to make this more useful in terms of like plotting and analyzing? Yeah, we can use Euler's formula, which I mentioned earlier, to kind of to convert it into a form that is very usable. So, without going into the massive details of how this converts, I'm going to show you what happens to this formula and what it ends up becoming through Euler's formula. So, if we use properties of exponents, then we can at least see this transformation, right? So I could break up the alpha and the beta into e to the alpha t, because you do have to distribute t into each term, and then e to the beta it plus c2e to the alpha t, like that. And then e to the negative bit, like that, right? So we have basically broken it up into two aspects, alpha and beta. And we also notice that they both share the same term, e to the alpha t, which means, well, I could just factor that out. And I end up getting something like this. But again, that I value is very, difficult to deal with in the context of analyzing real stuff. So we use Euler's formula. So using Euler's formula. And if you're wondering, well, what is Euler's formula? Well, there's different interpretations of it, but the most common one, if I can grab it real quick, is this, which is e to the it is equal to cosine t plus I sine t. Okay. So, and if you notice, we have an e to the it within that bracket. Um, we get the solution y equals e to the alpha t. And instead of having imaginary exponentials, they become cosine and sine. No more imaginaries. It doesn't matter which one comes first, sine or cosine. I typically probably do cosine first, but I've been known to swap just randomly on accident, so it's the same thing. It's all nice. And notice where alpha and beta come from that. So the cool thing is if you know one of the roots, you automatically know the other one because of the conjugate property. But also, you don't need to know both of them. You just need to know one of them. One of them gives you the answer. Now, what is really cool about the complex property or the complex case is it's probably the most engineering focused one. And what I mean by that is if you look at the equation itself, right, and this is kind of a peek into 3.7, which is a really fun section. Notice that the solution has e to the alpha t, right? And depending on alpha, right, you could have three different cases. So if alpha is a negative number, what happens is, well, sine and cosine's a wave, it just goes up and down. But what the exponential function does in the context of, what we're going to learn is mass spring systems, we call it a damper. It removes energy. So basically, our system will start to settle down. It'll basically remove energy. It's like, so if you're moving a spring back and forth, friction will slow it down until it stops, right? If alpha is positive, then we're adding energy to the system and it's doing this. It's just getting bigger and bigger. So basically, the spring is bouncing back and forth, getting faster and faster. And, if this is like a building, eventually the building collapses, right? Because it breaks apart. Too much energy. And then if alpha is equal to zero, well, what does that mean? It means there is no damper. That's what that usually means, is there's no damping. And so however you start is how you behave the entire time. And that's kind of what we call like the steady state solution. It's just what happens when nothing is going on. And then eventually when we add the non-homogeneous component, we'll look at how basically the system behaves in the beginning, and then in the long run, how does it behave, right? So like that's going to be the future case of like, what does that mean? But if you're wondering, what do I need to know to be able to be successful on this exam, and what is the formula I need to memorize? It's this one. That's it. Just got to memorize that. That's all it is. Now, going back to the imaginary part, I forgot to mention this. Um, Alpha is called the real part, and beta is called the imaginary part. Okay. So just in case those come up, they're often called the real part and the imaginary part. So you might see this notation, you might not. It just depends. So if you ever see like the real, so like these like capital R and then like E of R, they're just saying alpha. And if they say like I am of R, they're just asking for beta, right? So that's just a notation that might be used. Um, Actually, I'll just put beta I for the imaginary part. Nah, we don't need to. Yeah, there we go. So just in case that notation comes up, they do use that notation a lot when you're deriving it or proving it, but you should be fine. It's not going to be critical or anything. So, but this is going to be the case of damping when we do mass spring systems and we look at problems related to that. Now, if we're talking about solving a generic problem, the good news is it's pretty straightforward. Nothing too spectacular about this. So, solve the differential equation y double prime plus 4y prime plus 7y equal to 0. So it's the same four steps. That's the best part. The only thing that changes is step four, where you just have to choose a different solution. So step one, formula. What's the formula? AR squared plus BR plus C equals 0. Y double prime is equal to R squared. Y prime is equal to R. Y is equal to 1. That doesn't change. So when you're looking at how many sections you have in this exam, 3.1 and 3.8, there's no 3.6, I believe. 3.1, 3, and 4, they all follow the same four steps. 3.5 still does this, but one extra step at the end of it. 3.7 still does this, just word problems. 3.7 is the word problems of 3.1 to 3.4. 3.8 is the word problems of 3.5. That's what it really comes down to. So it's really three actual sections when you think about it. So not as bad when you think about it that way. Right? Now we're going to plug in. So we plug in and we get r squared plus 4r plus 7 equals 0. And now we just solve. Solve quadratic. Now, I'm going to do this over here because I know I'm not going to have the space. This is one of those things where if you tried factoring it, immediately you would not be able to do it. 99.9% of people can't factor complex roots. They're very difficult. So this is one you have to use the quadratic formula. So you do need to know how to use the quadratic formula because this is one of those cases where you kind of have to use it. So r is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. A, b, and c. So negative 4 plus or minus the square root of 4 squared minus 4 times 1 times 7 all over 2 times 1. Negative 4 plus or minus the square root. 16 minus 28, I believe, right? Yeah. And I get 12 over 2. And then my answer is negative 2 plus or minus 1 half square root 12. Whoops, I forgot a negative. Complex, duh. So what happens when you have a negative inside a radical? You just bring an I outside. That's all you do. Now, you don't have to do this, technically speaking, okay? But you can simplify radicals if you feel comfortable. It just makes the answer look nicer. But Edfinity shouldn't have any issues taking an ugly answer. So how would you simplify square root 12? Um, it goes back to like whenever you learn factor tree. Believe it or not, I learned the factor tree in like third grade. Um, you just take a number and you make a little tree and you say, what multiplies to 12? Well, 2 times 6. Okay, what multiplies to 2? 2 and 1. That's not any different. Okay, what multiplies to 6? 2 and 3. Basically, you're doing a prime factorization. I didn't learn it as prime factorization. I just learned it as a factor tree when I was younger. And then the trick that we were taught is you can circle any pairs together and then you get to yank it out of the radical. So then I get negative 2 plus or minus 1 half I times 2 square root 3. Whatever doesn't get paired up stays back inside and you multiply, right? And so these cancel each other out. And then I get negative 2 plus or minus I square root 3. It is recommended you put the I in front of the square root versus behind, just so you don't think it's inside the radical. But there you go. That's my R1 and R2. And then step 4 is classify solution and plug in. So this is not real roots, it's complex roots. So then that means my solution is e to the alpha t c1 cosine beta t. Did I put t in the answer? I did, okay. Plus c2 sine beta t. See if I can give myself more space to write that a little bit bigger. Alpha, sorry, r is equal to negative 2 plus or minus I square root 3. That's alpha. That's beta. So then y is equal to e to the negative 2t. C1 cosine of square root 3 times t plus C2 sine square root 3t. And that's the answer. That's it. If you compare it to the real roots case, you will realize it's not any different. It's just a different formula and just another one that I have to remember. And that's how you do a complex problem. So now let's just do like every variation that they can kind of throw at you to mess with you. So here's an example. Solve the differential equation. So what happens if they remove a term? Is it any more challenging? No, just, again, more likely to just trick you if you're not paying attention. Well, 0. So step 1, formula. AR squared plus BR plus C equals 0. Y double prime equals R squared. Y prime equals R. Y equals 1. Step 2, plug in. So 25 y double prime will become r squared. Now, here's the part where people mess up. If you plug in r for y, you will not get a complex answer. You'll always get a real root. So this is one where people will completely miss the question because they put the wrong term in for y instead of y, they put the y prime term instead of y. So it's just 750. There's no r there. And then step three is solve. Solve quadratic. Now this is a nice one because I can just isolate r squared. So I'm going to divide both sides by 25. So 750 divided by 25 is 30. And then r squared is equal to negative 30. And then if I take the square root of both sides, I get r is equal to plus or minus the square root of 30i. Like that. Again, do you need to simplify the radical? No, you can, if it's even possible, which in this case it actually is, I believe, right? 30, 2 and 15. Nope, it's not. Can't even do it because there's no pairs of values, right? So square root of 30 is as simple as it gets. And then step four is plug into solution. So R is equal to alpha plus or minus beta I, which is equal to I square root 30. Actually, let's not do it this way. Sorry, plus or minus I square root 30. So that's beta. And then, no, I'm trying to make it. So alpha is equal to 0. Beta is equal to square root 30. There we go. And then y is equal to e to the alpha t, c1 cosine beta t, plus c2 sine beta t. So be careful. Remember, e to the 0 is not 0, it's 1. So then y is equal to, there is no exponential component, just goes away. So then we get c1 cosine of square root 30 of t plus c2 sine of 30 t square root. And there you go. Will you ever have negative numbers inside of the parentheses? No. I mean, you can. So technically speaking, you can have negatives, but sine and cosine are kind of interesting functions because they're even and odd functions. So you can actually manipulate negatives inside and outside of a cosine and sine. Cosine, so again, kind of a tangent. The cosine of negative x is equal to cosine of x. So like the negative inside doesn't even matter. So this is actually thinking as an engineer. If you ever see a cosine negative x just randomly come cosine x, it's because they use the even property, but no one ever says it out loud. Um, and then the sine of negative x is equal to negative sine x. So you can just yank out the negative and it's still fine, right? And then it can be absorbed into C2 or whatever the coefficient is. So you'll never see negatives inside because it's not really uh, going to cause an effect. It can happen. It's just if it does, you can get rid of them kind of easily. So there you go. That's the solution. Are you wondering, if you're wondering, can there be a case where you have like y double prime and y prime? No, because it's always a real root. You can't make that a complex root. It has to be a real root. So when it comes to imaginary or complex problems, these are the only two cases that you can run into. It's where they don't give you y prime. They can only give you y. So that's kind of nice. There's only two cases. So that's really all it is. All we have to do now is just show an example of initial value problem, right? Solving for C1 and C2 when we need to plug in our initial conditions. So that's what we're going to do next. These can be just algebraically intensive if the numbers don't work out nicely, but also the thing that people struggle with and they just mess up a lot with this problem is the chain rule, right? So just to remind you, the derivative of the cosine of g of x, so like a function inside, actually let's just use u, that's kind of a common notation. Cosine of u is the sine of u times u prime, right? You take the derivative of the outside times the derivative of the inside. And the derivative of the sine of u is equal to the negative cosine. No, cosine's negative sine. Sine is positive cosine. There we go. And then u prime. Just chain rule. You got to use it. People mess this up all the time. All right. Solve the differential equation y double prime plus 6y prime plus 10y equals 0, given y of 0 equals 3. And believe it or not, in my experience, personally, solving for C1 and C2 for sine problems and cosine problems is almost always the easiest of all of them because the line between them being super easy and super difficult is very like fine. If I don't give you a nice value for sine and cosine, the problem becomes exponentially more difficult because it either evaluates nicely or it doesn't. There's no in between. So generally speaking, you should get nice coefficients on the exam for sine and cosine because otherwise they'd be super ugly. They're either very, very nice or super duper ugly. There's no in between with these, unfortunately. So they err on the caution of on the side of make them look nice. Step one formula. Like that. And from there, we know that y double prime is r squared, y prime is r, y is equal to 1. Step two, plug in. Again, it's complex, can't factor. We already know that ahead of time. And so we get r squared plus 6r plus 10 equals 0. Step three, solve quadratic. And so we're going to write our quadratic formula right here. So there's our quadratic formula. And from there, we get -6 plus or minus the square root of 6 squared minus 4 times 1 times 10 all over 2 times 1. -6 plus or minus the square root of 36 minus 40, so -4 all over 2. And so -6 plus or minus 2i over 2. So -6 plus or minus, nope, that's incorrect. -3 plus or minus I. And that's our value. So that's R. And then step 4, I'm going to go to the next slide. So step 4 is a plug into solution. So R is equal to -3 plus I, that's alpha, that's beta. So y is equal to e to the -3t, c1 cosine of t, because it's just 1, nope, incorrect, plus c2 sine t. So there is no chain rule in this one, thankfully. Should have done one with the chain rule. And step 5 is solve for C1 and C2 using y of 0 is equal to, you know it's a nice one when they give you like pi and pi over 2 usually. Like that. So you are going to take a derivative. So y is equal to e to the -3t. So this is going to be a product rule, which is never fun. Um, like that. And so our derivative. Now you can distribute and do the product rule later, or you can do it now. So f prime g plus fg prime. So 3 negative e to the 3t, so that's f prime. And then we write the g plus f, so that's just e to the 3t negative, times g prime. So the derivative cosine is the negative sine, and the derivative sine is the cosine. And again, you would do the chain rule if there were numbers inside of the parentheses of t. Okay. And then now you just plug in your value. So y of 0 is equal to e to the negative 3 times 0. Let me do it this way. So in this class specifically, but if you're an engineer, you need to know what the sine and cosine of 0 are. They are that important. So cosine of 0 is equal to 1. Sine of 0 is equal to 0. You just got to know those. They come up so much. So then we get 3 is equal to, this is 1. C1. Actually, let's not skip that step, I guess. So 1. C1 times 1 plus C2 times 0. So 3 is equal to C1. A lot of the times with the trig ones, one of the equations gives you an answer, like it's free, I would say. And then y prime of 0 is going to be 7 equal to. I wait till the very end to plug in C1, so even if I already know what it is, I just wait. You're going to get negative 3 e to the 0. I have to cut down a little bit of this because it's too much writing. C1 cosine of 0 plus C2 sine of 0 plus e to the 0 and then times negative C1 cosine of 0. I have no room here. Let me give myself a little bit more space, as much as I can. The negative plus sine, oh, can't forget the C2, plus C2 cosine of 0. And so then 7 is equal to 1, C1 plus 0 plus 1, and then 0 plus C2. So that's what you end up getting. And I think I can move this all up a little bit. I get 7 is equal to C1 plus C2. I want to make sure I didn't miss anything. I did miss a number. I forgot a negative 3 right here. Because e to the 0 is 1, but the negative 3 is still there, right? So negative 3C1, which then means 7 equals negative 3 times 3 plus C2, which means C2 is equal to, if you add over the 7 with the 9, you get 16. I believe that is the correct answer. And it is 16. And so the final answer, thus, y is equal to e to the negative 3t. C1 was 3, so 3 cosine. It doesn't matter that cosine goes with the 3, and then 16 goes with the sine. So like that stuff does matter. And that's the process of solving a complex problem. The way I make this more difficult is just make the numbers nastier. I make C1 and C2 more difficult to deal with. I make the coefficients more difficult so that the quadratic formula is more difficult. But the process itself never changes, just the numbers that I can give you to make the process more difficult. In the future, this is probably the most important version of the three cases in terms of physical applications, like spring systems and all that. Like I would say that this is probably the one we use the most because it's the most applicable to engineering and mechanical problems. But all in all, that's the last case that we have to investigate is the repeated roots. Repeated root is both easy and difficult. It's easy to work with in the sense of like mechanically kind of to do it, but it's difficult to understand where things come from. And sometimes the modifications can be very annoying if you have to, but that will be in 3.4.